Hello everyone. In the last section, we have introduced convolution layer. In this section, we will talk about pooling layer. Convolution layers in a convolutional neural network systematically apply learned filters to input images in order to create feature maps that summarize the presence of those features in the input. Convolution layers prove very effective, and stacking convolution layers in deep models allow layers close to the input to learn low-level features, and layers deeper in the model to learn high-order or more abstract features, like shapes or specific objects. A limitation of the feature map output of convolution layers is that they record the precise position of features in the input. This means that small movements in the position of the feature in the input image will result in a different feature map. This can happen with recropping, rotation, shifting, and other minor changes to the input image. A common approach to addressing this problem from signal processing is called downsampling. Downsampling can be achieved with convolution layers by changing the thread of the convolution across the image. But a more robust and common approach is to use a pooling layer. A pooling layer is a new layer added after the convolution layer. Specifically, after a nonlinearity, commonly ReLU has been applied to the feature map's output by a convolution layer. For example, the layers in a model may look as follows: input layer, convolution layer, ReLU layer, and pooling layer. The addition of a pooling layer after the convolution layer is a common pattern used for ordering layers within a convolutional neural network that may be repeated one or more times in a given model. Why to use pooling layers? First, pooling layer is used to reduce the dimensions of the feature maps. Thus, it reduces the number of parameters to learn and the amount of computation performed in the network. Second, the pooling layer summarizes the features present in a region of the feature map generated by a convolution layer. So, further operations are performed on summarized features instead of precisely positioned features generated by the convolution layer. This makes the model more robust to variations in the position of the features in the input image. In pooling layer, a lower resolution version of an input signal is created that still contains the large or important structural elements without the fine detail that may not be as useful to the task. The pooling operation is specified rather than learned. Two commonly used pooling layers are shown below. Max pooling. Max pooling is a pooling operation that selects the maximum element from the region of the feature map covered by the filter. Let's look at an example. Here we have a rectified feature map. Now it's going through a pooling layer. We set the max pooling with a 2x2 filter and a stride of 2. So we will reduce the rectified feature map down to a 2x2 pooled feature map. How to calculate? In this case, we took filter to be 2, and we get 4 values, 2, 3, 9, and 4 to choose from. From those 4 values, the maximum value there is 9. So we pick 9. We need to move the filter across the entire image. The procedure is exactly as same as above, and we need to repeat that for the entire image. Thus, the output after max pooling layer would be a feature map containing the most prominent features of the previous feature map. Average pooling. Average pooling computes the average of the elements present in the region of the feature map covered by the filter. Thus, while max pooling gives the most prominent feature in a particular patch of the feature map, average pooling gives the average of feature present in a patch. The size of the pooling operation or filter is smaller than the size of the feature map. Specifically, it is almost always 2 by 2 pixels applied with a stride of 2 pixels. This means that the pooling layer will always reduce the size of each feature map by a factor of 2, reducing the number of pixels or values in each feature map to 1/4 the size. For example, a pooling layer applied to a feature map of 6 by 6 will result in an output pooled feature map of 3 by 3. The pooling layer reduces the number of parameters to learn and the amount of computation performed in the network. After feature extraction, there are one or several fully connected layers. A fully connected layer is the basic layer found in traditional artificial neural networks. Each node in the fully connected layer multiplies each input by a learnable weight and outputs the sum of the nodes added to a learnable bias before applying an activation function. The number of connections between layers is determined by the product of the number of nodes in the input layer and the number of nodes in the connecting layer. The objective of a fully connected layer is to take the results of the convolution or pooling process and use them to classify the image into a label. First, we should flatten the matrix into vector. This step in the process is called flattening. Flattening is used to convert all the resultant two-dimensional arrays from pooled feature maps into a single long continuous linear vector. Then the flattened matrix is fed as input to the fully connected layer to classify the image. As we know that each convolution and the pooling layer contains a rectified linear activation layer as its output, we always apply softmax activation function after final fully connected layer. The softmax layer is integral to multi-class classification problems. The softmax activation function outputs a normalized form of its inputs. By doing so, it ensures that the sum of its output is exactly equal to 1. This allows multi-class classification to choose the index of the node that has the greatest value after softmax activation as the final class prediction. We take an example to explain the complete process of recognizing an image using CNN. Here's how exactly CNN recognizes a bird. The pixels from the image are fed to the convolution layer that performs the convolution operation. It results in a convolved map. The convolved map is applied to a ReLU function to generate a rectified feature map. The image is processed with multiple convolutions and ReLU layers for locating the features. Different pooling layers with various filters are used to identify specific parts of the image. The pooled feature map is flattened and fed to a fully connected layer to get the final output. This is the end of this section. Thanks for watching and welcome to the next period.